Hello, this is our rocket design project, and our team members are Jocelyn Acosta, Dora Muñoz, Edna Armas, Kevin Loya, and David Burciaga.
Now, on the brief background on rockets. In the 1200s, it is believed that the Chinese were the first to develop rockets that were used as fireworks. In the 1800s, the British developed rockets to be used as military weapons. In 1942, the very first rocket to reach space was a V-2 missile, which was launched by Germany. In 1950, the US combined German and American technology to launch its first two-stage rocket.
Hello, now I'll be presenting the development process that took to developing our rocket. So upon deciding on a design, we chose a design similar to the one shown to the right. Here in the right, you'll see a very basic rocket with its rocket components here described here by NASA. The components including just the basic body of a rocket, the nose cone, fins, as well as the four major components or major systems that are included in a rocket or should be taken into consideration while creating a rocket. So while doing our research, we learned about the four major systems needed for a rocket to go into space. The systems included the structural system, propulsion system, payload system, and guidance system. The structural system would involve the frame of the rocket, which would allow for it to hold the rocket's fins, cone, and body, while the propulsion system would include the fuel oxidizer and oxidizer. Now, the payload system is anything that the rocket would be carrying, such as its personnel. Lastly, the guidance system provides much of the information needed for the rocket to go and have a safe trip, such as the computer and the satellite, for it to have a stable trip. In continuation, in the development process, we learned that the ideal rocket would break apart into different sections in order for it to have a successful launch into space. The way this rocket would work is by allowing itself to reduce dead weight in the staging process. This staging process is, as mentioned, the method that involves breaking off large parts of the rocket into other pieces, typically like 2 or 3. There are several things that are taken into consideration while designing and building the rocket. For example, the fins of the rocket are crucial in order to keep the rocket straight. Without the fins, the rocket would be falling over. So, in order to prevent the rocket falling over, we considered the following, which is the size, the number of fins, shape of the rocket, and where/from it would be launched from. The location of where the fins would be placed, the location of where the fins would be placed is important as well. So our fins were placed at the rear of the body. This is just one of the things that we are mentioning here, but of course, while designing and building our rocket, we took into consideration the size of every component, such as the cone, the body, and even the individual fins. The shape of the cone, as we're going to mention here below, the cone of the rocket is just as important. Our rocket had a semi-curved nose cone. By it being curved, it would help with minimizing the friction as it would ascend upwards. As mentioned earlier, the location of / where it would be launched from. In our case, we did launch our rocket from a launching pad, but the location what we're referring to is the where the launch pad would be placed. So if the rocket launch pad was placed in a very rocky surface that would, of course, deteriorate the ability for it to go straight upwards into the atmosphere.
So these are images of our rocket. Rocket 1 was actually a rocket that was made out of cardboard. That's actually the rocket we lost somewhere in the desert. That one was pretty simple. The actual shaft for the rocket was made out of a paper towel roll, and then the wings and the nose cone were made out of a harder cardboard. Rocket 2 was made of PVC. After we lost Rocket 1, we decided to make a second one, and the second one we made it a little bit more sturdy and made it with a little bit more of a rigid design. And the base, we bought it just from Target. The materials we used in our rocket, which was the launch pad. We used the Estes B64 rocket engine, compressed cardboard for Rocket 1, and then afterwards PVC pipe for Rocket 2. And then we used pretty much the same PVC pipe for the nose cone. This is the first rocket, which was the one we lost in the desert. The design was pretty simple. I designed it on Inventor. All it was one cylindrical piece for the actual shaft and 3 wings, which I was able to put on there with 3 separate planes across the cylinder. And then as far as the nose cone, it was just one revolution going all the way around. And if you can see to the right, it's just the top front right, and then the 2 isometric views of the rocket itself.
This paper is intended to present the design, construction, and simulation process of the rocket, which was powered by an Antes P64 rocket engine. The development of the entire project was constantly supported by the Autodesk Inventor Engineering Design Program, where the model of the rocket and its structures were designed. The steps that were used were the following. 1. Select the Start 2D Sketch option, followed by the Emboss option to start the rocket body. 2. The next thing is to select dimension, and the desired dimension is placed, adjusted. When finished, press the Finish key. 3. Then you click on the Revolve option and arrange the cylinder that is in the upper part of the rocket. In the upper part, add one more line with the line key, then select the Arc option where the desired angle is given from the upper point of the last line towards the first part of the rocket's body. To conclude with this step, click on Finish again. 4. Click on the Revolve option again, where the body of the rocket and its tip will be selected. 5. Look for the body of the rocket, which is a rectangle. Select the Project Geometry option so that the figure can no longer be seen in 2D, and click the Line option below to create the middle rocket fins from below the middle of the body to finish to its base. To finish, select the Finish option again. 6. Repeat step 5 3 more times on each side of the rocket. 7. For the fins of the upper part of the rocket, do something similar to step number 3. Select the line key from the upper part of the rocket body to a little before the third of the rocket body. 8. To conclude, color the rocket with a default option and select the part of the rocket that you want to color with the different shades that are an option.
Why we chose this design? After a lot of research about different designs, we concluded that a simpler design can help us make a rocket that wouldn't need a lot of different materials, bigger dimensions, or a larger launching base. Also, we thought that the simple design made the rocket look cleaner and smooth. After the launching day, we noticed that we didn't really face problems based on the design, so after losing the first rocket, we had to make another one, so we followed the same design and the same development process. For our calculations and results, first we had to find the maximum height, and as you can see here on the graph, is H max is equal to the maximum height, the one that we're looking for. H is equal to the actual height from the floor to the base of the rocket. V is equal to the velocity that we estimated it was equal to 6.5 meters per second. the angle, that it was equal to 90 degrees. So we plug in all the values on the equation that we use, that it was x max equal to h plus the velocity to the second power divided by 2 times gravity. So like I mentioned, the height was 30 centimeters, so we put 0.30 meters plus 6.5 meters per second square divided by 2 times 9.81 meters per second square, and our result was 2.168 meters. Then we calculated the vertical and the horizontal displacement. So for the vertical displacement, we used the formula y is equal to 0.5 times gravity times time in seconds squared. And based on the video, we noticed that it took the rocket 3 seconds to launch from the base until it got lost in the desert. So we used that value to plug it into the original equation, and our result was negative 14.715 meters. And the result was negative because our gravity was negative, because it was a vertical displacement. So we have to plug in our value as a negative value. And then for the horizontal displacement, our formula that we used was x equal to velocity times the time in seconds as well. So we plug in the numbers 6.5 meters per second times 3 seconds. So our value was 19.5 meters. So we have a little chart with the values. So for example, if our time was 0 seconds, our horizontal and vertical displacement was equal to 0. And for example, if the time was 1 second, our horizontal displacement was equal to 6.5 meters, and our vertical displacement was equal to negative 4.905 meters. And then, for example, if the time was 3 seconds, as we calculated, it was for our horizontal displacement was 19.5 meters, and for our vertical was negative 14.715 meters.
The dynamics of rockets. So we did apply most of the Newton's laws of motion while researching and doing the calculations for our rocket launching project. So here we did use just the first 2 Newton laws of motion because they are fundamental to this class. So here the first Newton law states, of course, that an object will change its motion unless acted on by an unbalanced force. So in other words, if it's at rest, it will remain at rest. If it's in motion, it will remain at the same velocity. So in our case, for our rocket, what we found was when a rocket is at rest while being on the launching pad, the forces are balanced. Therefore, the force of the launch pad pushing up would equal the gravitational force pushing down on the rocket. While it's in motion, though, there is an unbalance of forces due to the thrust of the rocket, resulting in an upward reaction. Now, the second law of motion says that force is equal to mass times the acceleration. In our case, one mass would be represented by the gases exiting the rocket engine. Another mass would be the rocket moving the opposite direction, and the force would be the pressure created inside of the rocket engine so that the pressure can accelerate the rocket one way and the gas the other.
Some challenges that we faced while working on a rocket as a team was keeping a steady communication because, since the pandemic started, everything has to be virtually, and it's harder to keep in touch when it's through a computer or through a phone. And in correlation to what I said, the team members' schedules did not coincide. So since we all had different schedules, it was hard scheduling meetings. and we all worked, so we didn't have time. We couldn't match our times to meet. And then the engine that we used was different from the one suggested. The one suggested was one from Amazon that was $15, but it was out of stock, so we had to buy another one, and we had to work with the one that we had. The day that the experiment was conducted, the wind was too strong, so we actually had to work on the experiment 2 days in a row because the first day the wind was too strong, so we couldn't launch the rocket. And the second day the wind was still strong, but not as strong as the day before, so we still had some trouble launching the rocket. And one rocket was lost in the desert. Our first rocket was lost in the desert, so we could only launch it once. What was learned? To create a rocket, we researched several different rockets and the history behind them. We became knowledgeable on the origin of rockets and the different purposes that they were used for. After completing the research, we learned how to design and create a 3D model using limited materials. The whole process of creating our rocket was a learning experience since we had to research how to do each step. Our overall experience as a team. Through this project, we had to learn how to divide our responsibilities and how to communicate with each other. Some team members were absent, so we had to work accordingly to the resources and the people that we had. Although we faced many challenges, working together virtually, the overall experience working as a group was pleasant.